Okay, this video is all about naming cycloalkanes, and you're going to find this is really very similar to how we would do it for normal alkanes. Really, the first main difference is the fact that because we're talking about cycloalkanes, you want to make sure you have the word cyclo in the name. So if I was just to do this, and I was to ask you, what's the name of that? Well, 5 carbons, pentane, but because they're in a ring, it's cyclopentane. Simple enough. And when we go on to this guy right here, 6 carbons in the ring, so cyclohexane. There is an ethyl group coming off here, and all the substituents that we've learned before, we treat them exactly the same way as we did when we first encountered them. So therefore, this would be ethyl cyclohexane. Okay. Now you remember one thing we said previously was you need a locator number for each substituent. And rings, at least mono substituted rings, it's a little bit different, because you don't need to put a 1 here, because really this substituent could be anywhere on the ring and it'd still be the same thing. So there is no number needed when you just have one substituent on the ring. When you have more though, you need a number for each one, because you want to know where exactly they are relative to each other. So if we just look at this guy, first off, if you guys can name the parent chain, it's cyclopentane. Cyclopentane. How many methyl groups are there here? Well, there are 2, so therefore we need the prefix di for the 2 methyl groups, so therefore dimethyl. And then we have to ask ourselves, well, where is each one? And as we've seen before, we want our substituent numbers to be as low as possible. So we wouldn't start counting here as 1, or here as 1. We start counting in one of these two. It doesn't really matter which one, because whichever way we go, we get the same answer, 1,2-dimethyl cyclopentane. Now what about this one down here? This one's very similar, but the issue is that both of our substituents are not the same. So here we run into a potential problem. I could number my substituents like this, but I could also number them like this. And whichever way I go, the substituent total is the same. So which one's right? Well, here's what you do. Let's just write the name out, forgetting about our numbers for now. So, which of these 2 substituents comes first alphabetically? Well, of course, it's the ethyl. So ethyl, I'm going to put a dash here, because there's going to be a number appearing here. I'm going to put a dash here, and another dash here, because there's going to be a number here as well. And then we're going to do methyl. And what's the parent name going to be? It's going to be what it was before. Cyclopentane. And the rule in this case is actually very simple. When you have 2 substituents, and you run into this exact numbering problem, in fact, there's only one of these is right, you always put the lower number on the substituent that comes alphabetically first when you have a choice. So therefore the correct name here is 1-ethyl 2-methyl cyclopentane, and not the other way around, because ethyl comes before methyl. Okay. However, when we move on to tri-substituted cycloalkanes, it's slightly different. Alright, so we're actually going to do the same thing that we did before. We're going to write the name out and then worry about the numbers in a minute. So let's have a look at a tri-substituted alkane, cycloalkane. Okay, let's look at this one now. How many rings are there? sorry, not how many rings, how many carbons are there in this ring? Well, there's 1, 2, 3, 4, 5, 6, 7. So that means our parent name is going to be cycloheptane. Alright. Now, do we know what our 3 substituents are? What we should do, we have ethyl, methyl, and 1, 2, 3 is propyl. So we know that first is going to be, so I can make sure I leave enough room here, ethyl, put a dash there. Then after that comes methyl, and then after this comes, man, am I going to leave enough room? Oh, just about. Okay, something ethyl, something methyl, something propyl, cycloheptane. Now, let's look at our possibilities. But before we do that, let's see what the rule is. The rule here is actually very simple again, and it's a rule that we've seen before. You want your substituent total, or the location number of all your substituents, to be as low as possible, just as we have seen before. Okay? And so what this depends on is simply where you start counting, because theoretically we could start counting in several different places. Now, I wouldn't start counting here, here, or here as carbon number 1. I want to start carbon number 1 on one of my 3 substituents. So what if I was to start here? 1, 2, 3, and 4. So there is one set of 3 substituent numbers. Now what if I was to start, say, here? 1, 2, 3, and 4. My numbers there are similar, but obviously they're not exactly the same. What if I was to do, say, 1, 2, 3, 4, 5, 6. Now can you guys see that for the green colour, that one's definitely out because I have a 6 here. And that brings my substituent total to higher than anything else that I have. So what that means is, out of my blue and my red, which is the colour that I go for? Well, if you said red, you would be right, because 1 plus 2 plus 4, which is a total of 7, is less than 1 plus 3 plus 4, which is a total of 8. So for tri-substituted cycloalkanes, there's a little bit of trial and error to figure out which the lowest substituent number total is. But you can see it's not difficult to do. And then all you have to do is just match the location number with the substituent. So for example, using the red numbering system, ethyl is on 4, methyl is on 1, and propyl is on 2. So here in tri-substituted cycloalkanes, it's not necessarily the substituent that comes first alphabetically that gets the lowest number. It may work out to be that way if you do this, but it's not always going to be the case. Now let's do another one, looking at a group that we haven't really touched on before, but I wanted to make sure you all see. The parent name here is, well, what is the parent name here? How many carbons in our ring? Well, of course, it's 6. So that is cyclohexane. We have 3 substituents like we did before, but the one I want to look at is this one down here. It says CH3 3 times. Now what that means is, if this is our ring, we have a carbon, and then coming off that carbon there are 3 more CH3s. So our substituent is this right here. It looks kind of like a crow's foot. Now there are 2 ways to name this. One way would be to use the naming convention that we saw last time. the other way is the common way. So there's the IUPAC way and then there's the common way. I'll just go through both. The IUPAC way is we look at the length of our longest carbon chain in our substituent coming off the parent chain. And that longest carbon chain is 2 carbons. So this means we have a substituent with its own set of substituents. So 2 carbons means ethyl. But what else is coming off that ethyl group? Well, there is a methyl and a methyl, both coming off carbon 1 of the ethyl group. So therefore 1, 1, di. Let's see if I have enough room here. Dimethyl ethyl. That's a 1,1 dimethyl ethyl group. However, the common name for this is, out of all the groups, is the one name that's most commonly known by its common name, which is tertiary butyl. Tertiary butyl because there are 1, 2, 3, 4 carbons. Tertiary because the carbon connected to the parent chain has 3 carbons coming off it, so tertiary. Oftentimes you'll see it written like this with a T up in the air. T-butyl meaning tertiary butyl. And what the T says is it's just something to do with, like I said before, the number of methyl groups coming off the carbon attached to the parent chain. Because of that, because the tertiary is not anything to do with the number of carbons involved, right? When it comes to alphabetization, in tertiary butyl you just use the B rather than T, unlike we saw in class with isopropyl where you use the I. Okay, as you can see, my low battery thing has come up, so I guess I better pause it whilst I fix this. Okay, sorry about that. We've just been talking about tertiary butyl, alright? So when we look at our ring, then we have a methyl, an ethyl, and a T-butyl. Remember, we'd said that for alphabetization purposes, the B is used rather than the T for tertiary. So, in terms of alphabetization, which one of these would come first? Well, it would be T-butyl, ethyl, methyl. Alright, so T-butyl, and looks like I might run out of room here. Ethyl, and then methyl. And if we just use the same logic we used before, if I do 1, 2, 3, and 4, and then, well, let's do 1, 2, 3, 4, 1, 2, 3, 4, 5, yeah, that isn't going to work. If I was to do this, 1, 2, 3, 4, 5, can you guys see the colour that is the one we would go for would actually be the red again? So, 4, T-butyl, oh, no, I know, balls, I'm sorry. Let's get rid of that. It shouldn't be a 4. That should be a 1, T-butyl, 4 ethyl, 2 methyl, cyclohexane. Does that make sense to everybody? I hope so. So what if I was to throw in, say, a halogen here? Let's just do that really quick before we move on to the last slide. What if I was to do this? Let's do this. Whenever you see cycloalkanes containing halogens, particularly bromine or chlorine, for some reason it always looks like the halogen, for whatever reason, seems to come first in the name. And that's not because of some funky rule saying halogens are particularly important. All it is that chlorine and bromine happen to have letters in their names that the first letter in the name happens to be very close to the start of the alphabet. So, for these guys, we just treat them exactly the same way as we would treat alkyl groups. Alright? Methyl, ethyl, bromine, when it's a substituent, is called bromo. And our parent chain here is cyclobutane. Now, I'm definitely going to run out of room here, so this is going to look kind of crappy. So apologies. Okay, more crappy than everything else. Apologies in advance. Cyclobutane. Alright. So first we would have bromo. That's bromo. And then we would have ethyl. And then we'd have methyl. Like I said, apologies for the messy looking thing here. So we can do 1, 2, 3. What if we were to do 1, 2, 3? Well, in this case, you can see that whichever way we go, we actually get the same total of our substituents. And when that's the case, we're going to fall back on our previous rule that says we give the substituent with the name that comes first alphabetically, the lowest number, and number everything else accordingly. So therefore, which color system would we use here? Would it be green or blue? Well, bromine comes first alphabetically, so we give it the 1. So therefore, 1 bromo, 3 ethyl, 2 methyl, cyclobutane. So you can see for halides, you just treat them the same way you would normal substituents. Alright, the last thing I want to talk about here is a little bit about stereochemistry, and this, at least right now, before we get into a more detailed talk about it, which we will do later on, we're simply talking about 2 terms here, cis and trans. Because if you make a model of cyclohexane like this, where the 2 substituents are on carbons 1 and 4, you can actually make a model where those 2 groups are pointing in the same direction, i.e. both up, or pointing in opposite directions, i.e. up and down. If you guys remember, the wedge here means up, pointing towards you, and the dash means down, pointing away from you. The question is, do you guys remember? Well, okay, so whether you remember, because we haven't gone through this yet. One is cis and one is trans. So when the 2 groups are pointing in opposite directions, as they are here, 1 wedge and 1 dash, those are trans. Okay? Trans meaning opposite. And so therefore, we would name this exactly the way we would name it as if there was no stereochemistry here, and then just stick the necessary words cis or trans on the front of the whole molecule. So if we were to name this without any stereochemistry, I'm hoping you could see what we would get would be a parent chain of cyclobutane, a methyl group on carbon 1 and carbon 2, so therefore 1, 2, dimethyl, cyclobutane. Cyclobutane. And because we said already that these 2 methyl groups are sitting opposite to each other, the actual name for this would be trans 1,2-dimethyl cyclobutane. Okay. Now if we were to go down here, this isn't cyclobutane anymore, this is cyclopentane, but the idea is the same. We still have two methyl groups. They're not 1,2 anymore, they're 1,3 now. 1,3. Dimethyl cyclopentane. But in this case, the two groups are pointing in the same direction. So therefore, cis. Now let's look at these guys over here. Here I had, in this molecule I had two dashes. Here I've got two wedges. Now for something to be cis, it doesn't matter if both are wedges or dashes. Okay, if it's two wedges, it's cis. If it's two dashes, it's cis. It's only trans if there's one wedge and one dash. It's as simple as that, at least right now. So can you guys see, if I was to name these two molecules without taking into account any stereochemistry, can you see that we would have the same name each time? Because we would have 1,4 dimethyl cyclohexane. Now obviously I can't have two different structures having the same name. These are actually two different compounds with two different sets of chemical properties, so therefore they need two different names. We have this one that would be cis, 1,4 dimethyl cyclohexane, and this one that would be trans, 1,4 dimethyl cyclohexane. And that is how we name cycloalkanes. Okay. Good night, or well, good morning.